Okay, we got
Okay.
excellent connection. Awesome, it works. Okay, so I will pub and yeah,
All right, wonderful. Thank you, guys.
I shared you guys the Zoom,
Okay.
I mean the YouTube link.
Oh, yeah. Yeah.
I see us. It's pretty cool.
All right. Wonderful, wonderful. How many viewers do you have so far?
One, I don't know.
We have 5. We
Five?
can wait until 3:05.
Sounds good.
So, a minute.
Yeah.
All right, Catherine, you got it?
Yep,
Okay, great. This is gonna be fantastic. But I'm gonna hop off, unfortunately.
sounds good.
Um, best of luck, y'all.
Thank you.
Okay. Hi everyone. Hi all the viewers. Welcome to the AI for Dummies Tech Talk. For during Blueprint Week. Yeah, so we're super excited to have both Nathaniel and um Madison here. I'm
Yeah.
sorry if I got your name said wrong. Um, and yeah, so the talk will be a little bit um about do you believe computers will take over the world? They're going to discuss roadmaps for various machine learning projects, dispel the myths associated with AI, and discuss ethics of computational intelligence. So I'll just hand it over to you guys.
Awesome. Thanks for that wonderful introduction.
Yeah, thanks, Catherine. Okay, I'm Madison. What can I say? I'm a graduate student at Northeastern University studying AI and education. My background is from MIT in electrical engineering and computer science. I still do a little bit of research in neuromorphic hardware as well.
Awesome. I'm Nathaniel. I am also a student at MIT. I'm an undergraduate student who is pursuing a degree in computer science. And I'm currently doing research, undergraduate research in computer science artificial laboratories at MIT, aiming to combat hallucinations in large language models. So those are us both. And by the end of this presentation, we want to expect you guys to have PhD level knowledge on any one of these topics. What we're hoping to get out of this presentation is a foundation, a launching point for everything that you're going to do in the future. So I want these presentations to honestly make questions out of your head as to where you can go after listening to us talk for the next hour or so. So without further ado, I think we can begin. Wonderful. So this is our table of contents. This is what we're going to be covering during the duration of our presentation. As you can see here, we're going to cover some definitions first. Then after that, we're going to dive into some approaches to machine learning. After that, we're going to look at some architectures. And to wrap it up a little bit, we're going to get into some pathways and resources. As a finale, we're going to talk about AI and machine learning today, dive into some of the myths, current state of development, as well as the ethics.
Ethics, yeah. We'll start with the definitions. Okay, so we have this bubble here, this bubble diagram representing different fields. You can see on the right there's data science, and data science is this interdisciplinary field that uses tools from other fields such as artificial intelligence, machine learning, and deep learning to extract knowledge and insights and meaning out of raw data. So if you imagine like a tree growing out of soil, the soil might represent this raw data that might just appear random. And the tree is this structure, this meaning data growing out of it. Artificial intelligence is this broad umbrella term that refers to intelligence that is artificial, simulated, in contrast to like biological intelligence, like the wet and squishy brain that I and Nathaniel have. Um, and machine learning is included within artificial intelligence. The part that's not machine learning, but is artificial intelligence, usually is rule-based systems, algorithms that are written by real humans, in contrast to machine learning, which is where these models are learning from data. And deep learning is a subset within machine learning that involves neural networks with deep layers, many layers, that can derive insights from complex, intricate data, such as images. And it's usually inspired by the brain's inner workings. Next slide. Cool. Yeah, since this talk is machine learning heavy, we can go over some machine learning vocabulary. For example, feature. Actually, let's start with instance. An instance is a single point of data or a single input. And it can take the form of like a data point, such as temperature or height. And it could also be like an image, an input image, or a more general observation. And then instances are described by a list of features. For example, you might have a cat instance that is described by its length, its height, its fur pattern, which may not be numerical, but it's still a feature. And what we usually like to do is classify, for example, images as or into different labels. So what the labels refer to is kind of the output variables that we're hoping to predict. Like if we're looking at a cat, we could label it as a cat or a dog or a car or an apple, things like that. But it could also be numerical outputs as well. And then the models are the machine learning models, these algorithms that are actually predicting, given these input instances, it's predicting the labels.
So now we can dive a little bit into why ML. ML is great. I can use for a lot of things. We're going to see in the future that maybe it should not be used for all things. Let's go over some of the things that it probably should be used for. Traditional programming follows a pretty consistent format. You have a program and you have an input. From there, you do computations and you drive your answer. A parallel to this in the somewhat cooking world would be, let's say you have an ice cream recipe. Well, in order to make the ice cream, you need your ingredients. So the ice cream recipe is your program, and your input are your ingredients. You go through the process of following the rules, and then you make your answer, which is your ice cream. Now, what if you don't have all the rules? What if you don't have your ice cream recipe? Well, that's an instance where machine learning could come in. Let's go back to ice cream analogy. Let's say your grandfather has this amazing ice cream recipe. You remember as a child that you just love this ice cream, but he's passed away and he never wrote down his recipe. So what are you going to do? Well, let's say somehow you have this ice cream and you also have the ingredients. Machine learning can do this. What machine learning can do is find the connection between your input, which is your ingredients, and your output, which is your ice cream. It's going to make these rules for you. It's going to reconstruct the recipe based on the input and output. As you can see here in the diagram, in machine learning, which is going to be this second tab, you have a machine learning training program and you have your training data. This is used to create your model. From this, you take your model and then create testing data. This testing data is what's going to be used to generate your answer. As you can see, this part is a more twofold process than traditional programming, which is simply program input and computation. Now, ice cream is cool, but what about a real world example? What's a scenario where we cannot code all the rules? I think one, driving. What are some rules for driving? Well, you can't cross the double yellow line. Gotta stop at red lights. Gotta stop at stop signs too. We can't hit things. What can't we hit? Can't hit a curb. Don't hit another car. Can't hit a person. Don't hit me. Don't hit a co-presenter either. Please no. That's a lot of rules already. And I don't even scratch the surface of all the possible rules of driving. This is one instance where making a machine that takes in all the rules that you've programmed is probably not feasible. because explicit program of all the rules of driving a car would take years. In fact, you probably would not even be alive by the time you're done. Not to mention the possible gaps and pitfalls that you're not able to account for. In this scenario, this is where machine learning can be used in order to figure out the rules that are too time intensive for you to explicitly put out yourself. Now, garbage in, garbage out is a saying often found within the machine learning community, and it's a very powerful saying with very few words in it. The essence of it is that your in is your data, and your out is your result. So if you have garbage data, you will have garbage results. Does that matter how complex, how engineered, how virtually flawless you believe your machine learning model is? Your architecture is underlying what's processing all this information. If your information is inherently flawed, you will get a poor result. Which brings us to the next topic of this presentation, feature engineering. Data scientists often use this in order to minimize the possibility of having that garbage out by making sure that what's in is not garbage. So here we see a table. In this table, we have some instances. There's me, the dinosaur, the chicken, and some features as well. But those are my pattern. We're in confidence when we consider a feature vector for each one of these instances. The goal of this is to have a machine learning model that's going to predict whether or not an instance is a human or not. In our training data, we're going to feed me into the model. Say a human should have these features. It should be featherless and bipedal. In our testing data, we're going to give it dinosaur and chicken. Now, because the only features it has to work off of are featherless and bipedal, this machine learning model is going to assume that dinosaur and chicken also fall under the label of human. But as far as I can tell, I'm a biology major, but that's not right. So what if we add another feature? Does not lay eggs. As far as I know, I do not lay eggs. Okay, so now we have a little more information here. This fills in the picture some more. Now our machine learning model can take not just 2 features, but 3 features. And third features, and very importantly, one that's not shared by the 2 other instances. So now when it sees these other 2 instances, it's going to notice that it does not have the feature of does not lay eggs. So as a result, I'll be classified as a human, and dinosaur and chicken will not be. But that's still not the full picture. In fact, it's very far from it. What makes a human is not just feathers bipedal and not lay eggs. So it's very important as we're choosing these features to make sure that we're getting as much of the picture that we need in order to make a good classification. Arguably, to find a new instance that fits into the same category of feathers bipedal and is not lay eggs, and it's also not a human.
Yeah, this gets into garbage in and garbage out. Like sometimes you'll have noise in the data. Like a cat in this instance is bipedal.
And it's also very important that we choose features that are relevant. If we have added another feature that said that we can all wear hats, well, that's not particularly helpful for this picture either. So it's fancy and how nice machine learning is, and figuring out how the architectures work is very important. It's also important to remember that no matter how much you do research on how the algorithms work and how well you make your model, if your data is not very good, your machine learning output will be very flawed. Let me talk about that a little bit. Let's dive into why this data can be important and what we can do with it after we have what we consider a good set of data. Here are some different approaches to machine learning, one of which is supervised learning. Supervised learning mimics the task that we set out to do in the very initial ice cream model. We're going to have our labeled data set, and we're going to have essentially what we're going to make our model out of. This data set with labels is going to be what the machine learning model uses to make the rules. And from here, we can start testing data in order to figure out if those rules are working properly. This is often used in finance forecast analysis, as well as housing market prediction. Another approach we have is semi-supervised learning. In semi-supervised learning, we're essentially trying to make up for what we lack. We're trying to take ourselves out of the pitfalls of having data which is partially not labeled. In this presentation, we're going to focus on supervised and unsupervised learning primarily. For supervised learning, we're going to be training without explicit class labels. That means what we're trying to get out of this are things such as clustering and finding relationships between data, instead of always predicting what the label should be. Reinforcement learning is where we're going to be making decisions through interactions and environment feedback. These are 4 different approaches to machine learning. There are more, but we're going to focus on supervised learning and unsupervised learning in particular. So, what is an application of supervised learning? The applications that we have here are regression and classification. Regression tasks are essentially going to predict the numerical value of an output based on an input, while classification is going to be predicting the label of a new instance. Let's dive in a little bit deeper as to some examples of regression and classification. So, one example of regression is linear regression. I'm sure many of you guys have heard of linear regression. You might have seen on your calculator the y equals mx plus b. This is essentially creating a linear equation to model relationships between variables. Polynomial regression is quite similar, except instead of a linear equation, we're now making a polynomial equation. How does it work a little more under the weeds? What we're looking at here is a method of linear regression called least squares regression. We're going to have this at data points, and our goal here is to fit a line of best fit to our set of data points. This line of best fit is represented in blue on this diagram. Our goal here is to fit this line of best fit to as many points as possible, thereby giving us the best approximation of data outside of our sample set. So how do we know what is a good line of best fit? If I look at this graph and put it a little bit above and a little bit below, with my eyes, I really could tell the difference. There is a numerical way of doing this, which is by minimizing the standard error. The error is what we consider these gray bars connecting the blue line to little red dots. By minimizing the amount of error for every single point, we're going to be able to find the line that best fits the entire data set and minimize our standard error. This is good for achieving information about data that's outside of our initial data set.
Yeah, and can I add that these regression models, they don't just tell us a prediction based on an input, they also give us a sense of how good the model is. For example, if you could just measure the average amount of absolute error, and that gives you a sense of uncertainty about your prediction. And there are also different types of regression models. This one's just a line, a linear regression. But if you look closely, it kind of looks more like a square root kind of curve, where it starts there and then kind of goes up like a sideways parabola.
Absolutely. So now we're going to dive into some classification architectures. We're going to focus on k-nearest neighbors, but there are also some other ones that can be helpful to know and research in the future. K-nearest neighbors is a non-parametric classifier using proximity to make predictions. Other words there. Non-parametric. What's that referring to? Well, we're thinking about parametric. We're thinking about statistical assumptions that are making about the underlying data. Non-parametric means that it's not making any statistical assumptions about the underlying data. On the other hand, naive Bayes is a probabilistic classifier, which is typically parametric, which means it isn't making a statistical assumption about the underlying data. The statistical assumption it's making is that all of our features are independent. This is why it's naive, as this is not always an assumption that we can make. Naive Bayes is a probabilistic classifier, which means that it relies on the theory of probability, which the idea that randomness plays a role in future events. K-nearest neighbors is often used for general classification, as well as finance forecasting. SVM is object classification architecture, which classifies using hyperplanes. Now, what is a hyperplane? A hyperplane can be visualized in a three-dimensional space as a two-dimensional plane inside the space. So if we have a point that's above our plane might fall into one category. We have a point that's below our plane may fall into a different category. That is how we can make classifications. Naive Bayes is often used for tick classification as well as sentiment analysis. Support vector machine is often used for tick classification as well as image classification. These models have a lot of applications that expand beyond what we talked about here. So I encourage you to look into a little more of how each one of them operate. So, what is k-nearest neighbors? I mentioned that it classifies based on proximity. So what proximity are we talking about? The k-value in k-nearest neighbors is essentially referring to how many points we're going to be looking at. Here we have a new point, which is we don't know what it is yet, but we're going to think that it's going to be positioned right here among the data points. Here, we have a k-value of 3. This means we're going to look at 3 different data points in order to make our determination of what this new data point is. In this case, with k-value of 3, we have what we consider it as a triangle, because out of how many things line from the circle, the majority of them are triangles. However, if we expand our k-value to 5, well, now the majority of things that lie inside of our circle are squares. That's interesting. Well, it can't be both a triangle and a square. So this is an instance that this is an instance of an issue that we have that's going to be what our training is going to solve. During our training phase, we're going to figure out what k-values fits our data the best. There's not a one set k-value that works best for every single data set, which is why, as we run this test over multiple data points, we can figure out which k-value correctly classifies points most often. Now, with the k-value, we're determining the points that we're looking at, 3 points or 5 points. In order to figure out what points we're looking at, we need to figure out what distance is. See which 3 points are nearest to the point we're trying to classify. We have 3 different distance measurements right here: Euclidean, Manhattan, Minsky. But in general, what you should notice here is that we're trying to figure out the most frequent class given a certain k-value. Here are some different distance measurements represented graphically. And now we're going to go on to another type of architecture. This is ensemble learning. So here we have 3 different measures of boosting following 3 different names. But what is ensemble learning? The idea of ensemble learning is to make stronger predictions by combining the predictions of multiple models. There are 3 different ways it's typically done: bagging, stacking, and boosting. Now, as you can see here, there are multiple models stacked on top of each other, which is essentially influencing the final output. This is a method of stacking.
And I want to note that these are actually different types of models too. So you have k-nearest neighbors on the top, naive Bayes, support vector machines, and decision trees. Yeah.
That's good. So with these different types of models, they are all unique. As a result, they will have to be trained individually. Now, this training method is going to be more computationally intensive than having one single model. Additionally, when things go wrong, it's going to be a little bit hard to pinpoint exactly what is making this final prediction incorrect, as it's not just one model to debug and figure out, it is multiple to figure out what's not going correctly. So solution to machine learning and getting a bad output is not just stacking different models on top of each other, while it can be helpful in certain scenarios.
I kind of like the metaphor of a classroom where you have multiple students who are kind of trying to figure out the correct answer to a problem, and none of them individually truly know the right answer. Bagging you can describe as different students come up with an answer, and then you just like average them together. Boosting is kind of like one person says something, and then the next person kind of like adds something to the previous person's answer, and like it corrects over time. And then stacking is kind of like the teacher coming in and hearing what all of the students have said and then just deciding based on the discussion what the best answer is.
It's a great analogy. So you can say if we're doing our testing phase, the idea would be we have an image in this classifier, and we're looking to get a final prediction, which is what type of image this is, what's inside this image. Our goal here would be to get dog out of all. So what's the applications of unsupervised learning? Here we have clustering as well as association. Clustering is where we're uncovering natural groupings within data for pattern discovery. And association is essentially identifying the relationships and patterns for decision-making process. Let's step into clustering a little bit more. So here are two different clustering architectures. K-means and hierarchical. We're going to focus on K-means in this presentation, but I encourage you to look into these other types of architectures on your own time. K-means is a clustering algorithm that assigns data points to clade clusters, and this is based on their proximity to centroids. A lot of words. What's it all mean? So your idea here is that your K is referring to the number of centroids you're going to start with initially. And this is also going to be what your grouping is going to be made around. K-means it's referring to the K number of clusters, which is your K number of groupings. So first things first, you're going to select your centroids at random. From there, you're going to determine which data points are nearest to each centroid. After that, you're going to move the centroid to the average of all the data points that are nearest to it. And then you're going to continue this process until the centroids no longer have any change. At which point you'll be able to determine that you have clusters in these areas. Now, there are some downsides to this. The final clustering is dependent on the initial centroid placement, which means that it is technically possible to end up with clusters that have 0 data points. It's important to know the pitfalls of each machine learning algorithm that you use. Instead of just thinking about it as having an output, you just also understand what's going on behind the scenes. So when your output is not what you expect, you know what to do in order to debug it.
I want to add that K-means, in contrast to K-nearest neighbors, this is an unsupervised machine learning algorithm or method or approach. And so we don't actually know what classes or labels that are best to use. This algorithm figures that out for us. And so you can see in the example, we have 3 different collections or clusters of data. So the job of the data scientist or the computer scientist is to run this algorithm, see if these clusters make sense, see if they have something similar about them. Back to image classification, maybe one represents dogs, another represents cars, things like that. So yeah, that's the main difference.
Absolutely. So I get into the fun stuff. It's all fun. But I think this is a very big buzzword nowadays, a neural network. So I'm going to break this down a little bit into what different types of networks there are, and then dive into an example of what a neural network is and what it can do. So neural networks. Multi-layer perceptrons are neural networks with layering for complex problem solvings. In comparison to a perceptron, a multi-layer perceptron has at least one hidden layer. We're going to get into the words of terminologies of hidden layers and so on and so forth in a couple minutes. CNNs, or convolutional neural networks, are typically used for image processing. They capture intricate visual hierarchies and patterns. RNNs, or recurrent neural networks, are drawing conclusions based on sequential data. LSTMs, built on what RNNs can do, and are able to capture long range dependencies. I think this all kind of culminates, however, in the transform model, which is essentially able to use attention mechanisms for better sequence processing. Now, when looking at the transform model and the context that we're referring to in this case, I think a very good analogy is for next word prediction tasks, where in order to figure out the next word of a sentence, you should figure out what the sentence is trying to say. The sky is blue. You want to fill in the word blue. Well, in order to figure out that the next word should be blue, we need to know that the beginning of the sentence is referring to the sky. RNNs and LSTMs have difficulties with this as text gets longer and longer and longer. As in order to figure out what the next word is, the very end of the body of long text, you also need to know a little bit of what's going to be occurring for it towards the beginning. And so transformer models have been very adept at capturing these long range dependencies and able to figure out, okay, I'm generating this next sequence, next token, next word. What is it going to be based off of? Generative adversarial networks, or GANs, are dual neural networks in collaboration, which are typically used in generating realistic images. Oh, that's kind of scary. That is a neural network. In terms of what this is used for, nothing to say, because neural networks have a variety of different purposes. But I think it'd be good to break it down a little bit into something a little more simple. This looks nicer. So what is a neural network? A neural network is a computational model inspired by the human brain. The neurons here are what we consider these colored circles, and the yellow, blue, green, and red are each examples of different neurons. Dendrites inside the human head are modeled as connections between these neurons right here. So now we're going to go into how this process actually learns a little bit. In the case for classification of what an input image is. So let's get started. Okay. All right. So take a second to get set up here real quick. Be back in about 1 minute. All right, so on the board behind me is a diagram. Hopefully this diagram can be seen online, and let us know if you can't. Okay. So this diagram is a diagram of a neural network. As you can see here, there are a couple of different parts of this diagram.
It's kind of tiny.
Not tiny?
Yeah.
Can make it any bigger. I'm not sure.
I think that's up to Catherine, but like, I think we can do a rest.
Can you do the rest? All right, keep going then.
If you want to draw a new model real quick.
You think so?
Just really large.
Bigger?
Yeah.
Really large? I think time purposes we have to keep a small model.
Yeah.
It's all right.
We'll make it work.
We'll make it work. Birch was not always the easiest, guys. It's all right. So in this layer right here, this is our input layer. Now, what is this input? Like I said before, our idea here is that we're trying to figure out what type of shape and images. So in this situation, our initial shape is going to be a circle. So in our input layer, we're going to be putting in this circle. Now, how do we get a circle into our neural network? Well, the idea here is that we're going to recompose it into a vector. How is this going to happen? Well, in the circle, let's consider it as a 4x4 image, which means that's going to have 16 pixels in total. Each one of these 16 pixels is going to represent a value between 0 and 1, which is going to be the activation inside of our initial layer. So this pixel right here is mapping to this 0.7 value is going to be this pixel right here, our activation of 0.7. So this entire image is going to map into our initial layer, which is our input layer of our neural network. And from here, information will be propagated through this neural network to the very end, where we're going to get into what it's supposed to be. So let's build this neural network. Each one of these neurons is going to have connections to the next layer. So right here, we have 1, 2, 3 connections. Here we have 1, 2, 3 connections. And here we have 1, 2, 3 connections. Think about that as happening throughout the entirety of this neural network. Instead of here, I've made a couple ellipses as to indicate that there should be 16 dots right here corresponding to the 16 different pixels here, but it's very hard to fit 16 pixels on the board. So think about the rest of the 16 minus 8 pixels as represented right side here. These are also connected to this next layer. So consider these as our hidden layers. This is our hidden layer 1, and this is our hidden layer 2. This is our output layer. We're going to analyze what our final value is. So how does information propagate through this neural network? How does it get from this neuron to this neuron, eventually to our output, which is going to be a value indicating which one of these is the correct classification? This is done through our weights. Now, our weights are our connections. Think about this as a small scale of our large neural network. This is simply a connection right here. So in this connection, we're seeing is that for this neuron right here, we're receiving the weighted inputs of both of these inputs. And this is how information is propagated through a neural network. Each one of these neurons is receiving a weighted sum of the activations from the previous layer, which is then propagated through the neural network to the very end. And as we get to the end, we're going to receive weighted sums, which are going to be these different neurons right here. And whichever neuron has the highest weighted sum is what this neural network believes is our input image. That's
Just add the weights, they can actually be negative too. So when you say weighted sum, that might think you might think of like 0 to 100% for each weights, but these weights don't have to be between 0 and 1. They can also be negative.
Absolutely. And as an important part to mention, in an ideal neural network, we're going to have something called feature visualization, which is where these negative weighted sums are going to come in. If we're trying to classify a circle, what we want to do is figure out what makes a circle. So potentially inside of this neuron right here, we'll be visualizing a semicircle. So this neuron is going to essentially be looking at that part of the image as the result of the culmination of things that came from before. And maybe this neuron right here is going to be looking at half of a semicircle right here. Now, how does it visualize half of this semicircle or this semicircle right here? Well, this is all going to be part of that weighted sum. If the weights around these other areas are made negative, it's going to be focusing on the weights that are positive. And as a result, the pixels that are lit up here are going to be what influences the weighted sum here the most. Along with that, we also have something called biases, which are going to influence our weighted sum and make it so whatever we get inside of here has to be of a certain value for it to be activated. So if we have a negative bias, well, we want to make sure that our weights going into our neuron are high enough to activate our neuron. That is a lot of things, and I encourage you to look into neural networks a little bit more in your own time.
Or the vision system of the human brain. This discussion is actually very similar. The human brain looks at really low-level curves, shapes, textures, and they combine into something more high-level, like this fruit, for example.
Absolutely. So now that we went over how information is propagated through the network, through our weights as well as our biases, which we would consider our parameters of this neural network, let's figure out a little bit on a high level how these parameters are going to operate and actually be changed in the long run. Well, essentially what's going to occur here is that if we have an input, which is a circle, and an output, which is also a circle, well, what we want to do in this case is figure out, well, is this correct or incorrect? If we have a labeled data set for our training, what we want is to say, if we have this image, its result should be a circle. If it is not a circle, that gives information as to where we need to go. So let's say that instead, this had classified it as a square instead of what we wanted, which is a circle. Well, that would inform us that the weights associated with square need to be lowered, and the weights associated with circle should be raised. As a result, from this information, we'll be able to conclude that what weights and biases need to be altered and changed, like knobs and dials, in order to make our correct classification in the end. That is our very quick and neural network demo.
Your battery's about to die, so
Yeah, so
I don't think that plug is working, so. You're trying to?
we got it.
Yeah.
Awesome. And a laptop battery that we're trying to get all nice and charged up to us so we can continue this presentation. And as my co-presenter is doing that, I'm going to be re-sharing the screen.
Lower.
Let's check.
Oh, I didn't know where it needed.
There we are. All right, and we're back. So that was a neural network in just a couple minutes. So there are a lot of different types of neural networks, as you'd imagine. We went into a couple of them previously, and here are some different diagrams that represent different types of neural networks. A lot, and very complicated, some of them. But each one of these complicated neural networks is important to understand that they all build on each other. So we brought up the multi-layer perceptron as an example, but that was built on the perceptron, which was then built on and built on and built on in order to make the big complicated ones. And this is a very important part to understand about machine learning and artificial intelligence. You can break down big problems into smaller problems. And while things may look very complicated at the very end, if you do proper abstraction and proper problem solving analysis, even the big problems can be made into smaller ones, which you can tackle yourself. So now we're talking about a little bit about generative AI. I know a lot of people have heard about ChatGPT, maybe the latest Sora model. Well, these all fall under the category of generative AI. And here are a couple of things called image generation, text generation, music composition, as well as video synthesis. The models that typically used for them have been appended below each one of their names.
Yeah. I can do that. That's fine. Image generation. Right. So this is the generation of images using artificial intelligence or machine learning. I want to start with Stable Diffusion because it's an open source model and you can actually get started with it on your computer or even your phone. There's this Draw Things app. Like if I type in a puppy playing baseball, for example, I can hit generate and I'll try and show it on the camera in a minute, but it takes a while, but it's like something you can do and I think it's really cool. The way Stable Diffusion works, yeah, thank you, is by well, first, the training phase kind of starts with two steps or two phases. First, it learns this. So from physics, there's this idea of diffusion where particles can like scatter randomly. And what Stable Diffusion models do is it takes a look at how a crystal clear, coherent image, for example, of a cat, can diffuse into random noise, like TV static that you see on the right side in step 4. So first it learns this process, this diffusion process. And then the second half of the training phase, is the reverse process of that. So it has to learn the reverse, starting with static, going into a clear, crystal, coherent image. And in this process, it kind of learns a latent space, this representation of any amount of images. And then after the training phase, we can start generating images. Either you can use that latent space to control the image output, or you can also train you can use something like clip to transform text into that latent space representation and generate images that way. And stable kind of refers to how the model must converge to a high quality output. It can't like switch up during the whole process. Yeah, let's go back. The Midjourney. So Stable Diffusion is open source. Midjourney is closed source, though it's pretty impressive. It's actually a Discord bot that you can join their Discord server and generate images. I believe they have like a free trial, and then it's like $10 a month or something. The image shown on the right was actually created by Midjourney, and it won this competition for digital artists. The artist was pretty clear about that it was made by Midjourney, despite like this, and then they won that competition, but artists were set up afterward, understandably. It just raises questions about, for example, why anyone would pay for new human-generated art when AI can do it in minutes or even seconds. Let's see. And also, Midjourney was apparently trained on like 100 million images that were just scraped from the internet. And you can't just get the consent of every individual artist, but there's also not even a way to opt out of this process. So that raises ethical questions as well, because in Ethics 101, at the very least, you should allow people to opt out of whatever you're doing. And there's also not compensation involved for these artists as well. So I'm curious what other people think. Yeah, and then Dolly is another image generation system. It's also closed source, despite OpenAI having open in its name. And it works by two components. It has this variational autoencoder. So it trains on images, which I kind of want to draw a picture. Maybe you can see this a little bit. The way an autoencoder works, you have like a neural network with a bunch of inputs, and then autoencoders like squeeze all that information into what's called this latent space. Is usually a lot less neurons than were from the input. And then the autoencoder's job is to recreate that image, that same image, but using less data, less information. And so it's kind of like the human brain, how that works. Because like, Nathaniel, I recognize you as a human, so there's like a latent space feature variable that's like, you're a human. I see objects around me, and that high level information is like compact into my imagination, into my thinking process. So Dolly, and kind of Stable Diffusion 2, is representing images through this latent space. And the other half of Dolly is it converts text using the same transformer architecture that ChatGPT uses into this latent space. And then you can, by taking advantage of that, I can convert text into this latent space and generate images that way. It's kind of an overview of how that works. Let's go to the next slide. Cool. These images are pretty cool. So if you look closely, you can actually see that. Oh, actually, I want to show. Can you show me on that? I want to show the little puppy playing baseball. Tell me how good this looks. Can you see it?
I can see it. As well, how well I can see, I can't
You
tell.
can do this on your phone. Maybe it's kind of tiny, but like, I think it's cool.
That's really
the
cool.
dog kind of has an arm growing out of its mouth, but like, it's cool.
I'm sharing my screen real quick.
Cool. Catherine, how much time do we have?
We have 7 minutes.
Okay, okay. I like this collection of images because it shows like signatures, scribbles, that were actually generated by AI. This was what is this called? Lensa AI, which is an app that can edit and generate images on your phone. And you can take two perspectives on this. One, these scribbles is just a messy combination, of the unethical use of the art that the models were trained on, and that lazy, apathetic process that didn't really involve ethics. But you can also take a positive approach. I think it's kind of cool that humans, over time, over millennia, we've been sitting down, practicing art, focusing our attention for hours at a time, and then we're getting better at it. We have digital art now, and now we have AI art, and it's kind of this. Maybe it's a beautiful conglomeration, and this in itself is kind of a work of art. Next slide. All right, Sora's text to video instead of text to image by OpenAI. I like this example because you can see the dogs morphing into each other. So yeah, it's also a diffusion model that starts with frames of random noise, I believe, and uses machine learning to gradually transform them into a video. Some limitations, it can only do up to 60 seconds long. It doesn't have sound. It has difficulty accurately simulating complex physics and understanding cause and effects as well. I think it's cool. All right, so text generation, just what it sounds. It's like text prediction. And it's the transformer architecture, which ChatGPT uses, is, as Nathaniel mentioned, it's this evolution that started from recurrent neural networks to long short-term memory neural networks. Now we have transformer models that have this attention mechanism that allow it to keep track of different elements at the same time. For the sake of time, let's continue. AI music composition, I think what I want to say for this is it raises questions about who owns the music. Is it the people who created the AI models? Is it the people who created the music that was used to train it? Is the music generated by AI still authentic? And this goes for AI art in general. Like if I feel something from AI generated music, does that mean it's authentic still? And so is that question about how this might affect jobs as well. File transfer is kind of cool. Back to the latent space idea. Some of those latent space variables might represent style, like the Mona Lisa is a painting, an oil painting, old, historic, and it has certain colors associated with it. I'm actually not familiar with the painting in the middle, but you can see that there's this geometric style of saturated colors. So what you can do is you can take the structure of the first image and the style of the second image, put that into an image generation model. And what you're essentially doing is transferring over the style. Okay, we'll get into pathways and resources. Yeah, as for classes, generally just like build a strong foundation in mathematics. For example, linear algebra that deals with matrices. We talked a little bit about weighted sums with the neural networks. A lot of linear algebra is involved in that. Calculus, statistics, which is kind of what machine learning grew out of. Algorithms, data science. I like research, so data science kind of gets me excited. Anything with machine learning or artificial intelligence as the course title in your undergraduate, like your classes, that's generally a good rule of thumb. I still actually remember learning about support vector machines and boosting and bagging from artificial intelligence from an MIT class titled that. And natural language processing is another class that I enjoyed at MIT.
All right, so some recording language really, really quick. Out of these three, I think you should really put a focus and emphasis on Python. Java, C++ are used. In fact, C++ is very good for high performance and low level optimization. When you're first starting out, I think it's good to grasp the basics and start out with Python. Java is good for enterprise application, and Python is just the most widely used at the moment.
Okay. Oh yeah, so the state of the art tools, essentially this collection right here. Maybe some of you have heard of NumPy and Pandas, especially when you're getting into Python. OpenCV is computer vision, natural language processing toolkit, scikit-learn, PyTorch and TensorFlow are particularly for training neural networks. All of these, I believe, are available in Python, but also written in C++ for efficiency.
Absolutely.
And then these are some examples of projects that you might be interested in getting into. For example, predicting text, that's natural language processing, housing price prediction. That's like a classic, like based on room size, for example, can you predict the price of a house? Image classification, you can use PyTorch. MNIST is the MNIST. That's a very popular data set. Facial recognition and gesture recognition using OpenCV. I feel kind of rushed, but spam email detection is another project. Okay, AI machine learning today.
So we spent a lot of time talking machine learning, and now I want to tell you not to use it, which is a little bit interesting because I mean machine learning is really cool and really important. However, it's not a solution to all problems. We talked about the very beginning, there's garbage data. You should not use machine learning because garbage is going to be garbage out no matter how much money you throw at your model. Along with that is deterministic issues. Models are built on something called stochasticity, which is that there is a element of randomness and it's based on probability. So there's never going to be 100% deterministic output. It'll be high probability, but if you want something to be always deterministic, machine learning is not the best path. Here are a couple of different myths about AI. I think that it'd be good if you look at each one of these individually and figure out why they're why they're myths. AI being complicated, as you can see, it's really going to be built on a lot of smaller things you can build up over the time as you try to learn AI. It doesn't have to be something big at the very beginning. AI can be 100% objective. Bias in data is going to be resulting in bias in results. So you can't say that AI is completely objective. It's always an objective source. And intelligence is very hard to quantify. So I think that you should look into some debates on quantification of intelligence. Jobs being replaced by AI, jobs be created and jobs be replaced. It's a very fluid type of interaction that I think is important to look into as well. This is kind of the state of the art, the state of the field right now, the state of what things are looking at, where we're hoping to go in the future potentially. You know about GPT? Talk about Sora, talk about transformers. Microsoft and OpenAI are kind of like a space race in order to figure out which one is going to be the best in the creation of machine learning models, artificial intelligence. And open source models are struggling right along behind and trying to make the best model possible without giant resources that are backing a lot of these private closed source companies.
A couple more slides. So we kind of mentioned a lot of the ethical discussions throughout the presentation, but these are three themes. Maybe it'll destroy jobs like customer service, for example. These AI models, they can generate misinformation, but they can also generate convincing information and within half a second, right? Just kind of scary. And the models will always be biased. I think that's just a rule of thumb that we have to live with, to be honest. And I kind of want to present some data that I've gathered. So I asked some MIT students, have you ever used generative AI? And I believe this was in December of last year. Most have, some haven't, but of those who have, actually, I think I asked everyone, you know about any of the risks or ethical issues? Most said yes. And here are some themes that I coded from that data. We have over-reliance, which includes misinformation, training methodology, which involves bias, but also censorship, how these models are used. Originality, which touches on copyright issues we talked about. informed consent, stolen content. Something I'm interested in as an educator is plagiarism, cheating, using these to complete assignments, but not really learn from the assignments. And how to use cite these models as well. And the last kind of theme is human devaluation. So job replacements, AI takeover, transhumanism. These are all the ethical discussions that I got from the survey results. There's a more positive side to these, more positive perspective to these. So instead of job destruction, you can think about jobs transforming or creating even. For example, collaboration with teachers. And yes, models can generate misinformation, but they can also be used for brainstorming and prototyping and storyboarding and creating designs. And yes, they're going to have bias, but you can also think about how these models are fine-tuned to specific contexts, and that makes them very valuable for those contexts. So back to the survey, I asked, like, what do you use these tools for? Most people said creating, brainstorming creative ideas. You can also see school assignments. I don't know whether that was for just completing them or actually learning from them. But you can also see learning about topics is up there and entertainment as well.
And yeah, these are the sources that we used. I want to thank you guys for listening in. Sorry that we had to kind of truncate the last slides of our presentation due to some time constraints. But if you would like to reach us, I think that you should, if you have any questions. These are our emails right there. And that is a link to our slides of the QR code. That's everything.
Thanks,
Yeah.
Catherine. Good luck
Thank
with
you so much.
tomorrow and Sunday as well.
Yeah, thank you.
Yeah. Thank you so much, Nathaniel and Madison. And yeah, we hope to see everyone at the Learnathon and Hackathon starting tomorrow. Bye.